Here are the questions that I asked ChatGPT about integration. So the first one was, what are the necessary conditions for a function to be integrable on a closed interval in terms of Riemann sums? Came out with the definition for Riemann integrable: boundedness, finite partitions, lower sums, upper sums, their equality. So, and I didn't check in gory detail that these conditions match what was in Wade. I was just getting started. Then, are there bounded functions that are not continuous? The answer, of course, is yes. It used the Dirichlet function as an example. And of course, I hope someday that these LaTeX bits will be shown the way it comes out pretty when you process the LaTeX, and not this way. It's a little hard to read. And this reminds me of something that I did before in Wade, where you add the Dirichlet function with a function that does the opposite, and you get f of x equals 1, which is continuous. So at every point for one function, 1 is rational, 0 is irrational. And for the other function that you add to it, you do the opposite. Sure enough, everywhere you get 1. And so, yeah, just nice little thing that I did back then. Can a nowhere continuous function be integrable? This is a little deep, and I looked this up a little further after I asked ChatGPT, and there'll be more down further on in other questions that I asked. But yeah, so it concluded a continuously integrable function must be continuous almost everywhere. So a nowhere continuous function cannot be continuously integrable. I didn't want to go down further. I just asked this. Is there a difference between Riemann integrable and integrable? I could have posed this question better. And it basically said yes. And also it mentioned Lebesgue integration, which I looked up a while back, and I'll get to in this cycle of self-teaching. Are there any nowhere continuous functions that are Riemann integrable? This is where it mentioned Thomae's function. I looked it up. I think I've already mentioned it in one of my updates. Put up the definition for it. So 0. So the first case is 0 if x is irrational, and then the fraction 1 over q if x is p over q, which is meaning it's rational. Yeah, I already mentioned this already in one of my updates, and so it is Riemann integrable. It's got a 0 integral, so it is defined. The integral is defined. It's 0 everywhere. What is the relationship between bounded on a closed interval and integrable? I misspelled it, but it still didn't punt, so it kept on going, which is really good. And so yeah, if a function is bounded on a closed interval, it may still be Riemann integrable. That's good. Yeah, this is not such a great question, so sometimes I'll ask the question because I'm trying to learn, but in hindsight, it wasn't the best question to ask. But it's only in hindsight after I've done some learning. Relationship between monotone functions and continuity. Use the Dirichlet function again. So yeah, so however, a monotonic function may still have points of discontinuity, such as jump discontinuities, which occur when the value of the function changes abruptly. Yeah, so it's a complex relationship. There's more, basically. Also mentions weakly monotonic. Yeah. So while strict monotonicity implies continuity, weak monotonicity does not guarantee continuity. Is the limit of an integral the integral of the limit? The answer I already knew was no, but I wanted to understand how I would show it. Again, someday I want to see, I would love to see this shown as processed LaTeX instead of raw LaTeX. Yeah. Yeah, it's not necessarily equal, but I did not ask for examples. I just wanted to see it, see the definition that it isn't. And of course, Riemann has great examples about this. Yeah, so I moved on. Sometimes, and what I want to point out here is that sometimes I'll ask a question, and I just wanted to ask a general question, and then I'll do some web searches, and I'll look at a book, and so I'm not completely relying on ChatGPT for everything. And also, I wanted to mention, these are just questions that I'm going to keep in a question bank. This is why I put them always in the description of the video. And so right now, it's not like I'm going somewhere. I'm kind of like exploring. What is a compact interval? And this is a point set topology question, and I'm going to go a lot deeper into that in the future. It gave me a straight up, full-on topology answer, of course, with the Heim-Borel theorem mentioned and everything. But I'm going to go down that path later on in my self-teaching of real analysis. And so gave me an answer, but then as it gave me the answer, I realized, all right, I'm going to ask this question some other time when I ask a bunch of point set topology questions. What are the different mean value theorems for integrals? It gave me 3. The one that we all know and love, the integral of a to b f of x dx is equal to f of c times b minus a. But this is also usually shown as f of b minus f of a. Then the second mean value theorem, which I think is also called the extended one, which has 2 functions, f and g. And gave another version of the extended one. So, yeah. And of course, now that I'm reading about Taylor series, they come out of the mean value theorem, which is a very interesting tidbit. For the second mean value theorem for integrals, what is the definition of a primitive function? And this is when I went down the path of the antiderivative, the capital F function, for the fundamental theorem of calculus. And yeah, this is just a description of the fundamental theorem of calculus. Yeah. When is a differentiable function not integrable? If it's not continuous over the interval of integration. Yeah. That's the bottom line. Yeah, so fundamental theorem of calculus for when a function is continuous and when a function is differentiable. Yeah, part 1 and part 2 of the fundamental theorem of calculus. This is where I got a little stuck with improper integrals, so I asked for the definition. And it's 2 types. I think they're even called type 1 and type 2. Unbounded intervals and singularities. And of course, this LaTeX. It's a little hard to read. So it's the integral from 1 to infinity of 1 over x squared dx. Yeah, you take the limit of 1 over x squared. I mean, you end up with 1 over x, and then you take the limit at infinity at 0. And then there's the integral that it used for singularities is the integral of 0 to 1 of 1 over square root of x. Yeah. Then it mentioned Cauchy principal value here, and this is where I looked it up, and it turned out, of course, that it was not some big new tool that I was going to use in the future, because I got some insights from handouts that explain why it's dangerous to use Cauchy principal value to try to calculate something out of an improper integral, where you just should have realized that at in that specific interval, there's just nothing to calculate. But I learned something. That's fine. Then I asked about the coordinate function in analysis. It's something that was mentioned. It's a term that I learned in Riemann, and I also mentioned it in the book video that I did about Riemann recently. So yeah, this is where it showed me what the coordinate function does, and this was instructive. So again, learning from ChatGPT. It has a different definition than the one used in Riemann, but at least it showed me what it did, what a coordinate function does, and that's what I was really going for. What are all the types of integrability for improper Riemann integrals? And this is where it goes over the type 1 and type 2, the unbounded interval, and yeah, so this is on an unbounded interval, e to infinity, and then on a bounded interval with a limit. Again, I can't wait for these LaTeX expressions to be shown in ChatGPT in a readable format. Yeah. And of course, you can get divergent integrals when you're trying to calculate improper integrals. Then the bounded variation special section in Wade talked about, how much does a function wiggle? If it varies a lot or if it varies very little. And so it went on, very, very interesting description of it, of bounded variation. I took notes of this. Then I asked it for examples of function variation that are not a bounded variation on a closed interval, and how that variation can be calculated. So I was trying to figure out, how do you calculate it when the function oscillates too much. And so, of course, it gave me some really good examples. The best one is number 4, square root of x times sine of 1 of x. And so it oscillates infinitely. So it's not a calculation. It's more like you describe what it does. That's sort of what you substitute in for calculation. Went on in a lot of detail, so this was really good. This was very, very useful. And again, the questions are all in the chat and the description of this video for you all to try. And that's why I don't go into every gory detail or type the commands into a live ChatGPT window. I hope this was useful to you.